Okay, good afternoon. I'd like to remind you again that exam 3 is coming up. And those of you who have taken the second optional exam, I have not been able to get around to your exams. So I should have them hopefully by tomorrow or by Wednesday. So I would like to remind you that I posted some notes on solving the Atwood machine and inclined Atwood machine. And I will repeat it for the nth time that inclined plane will show up in one form or the other on the exam, right? So if you are unable to do that, that's on you. So I will be very clear about that. So inclined plane will show up in one form or the other, right? And then there is also projectile motion, and all the notes is uploaded. It's under reading materials. And I also posted a study guide under practice exam for exam 3, the concept that you need to revise. We started with chapter 5 in the last lecture. My hope is to finish most of chapter 5. I also posted homework 5.1, and I also went ahead and posted solutions and hints for the homework so that you can get more practice. My suggestion would be not to look at the solutions and hints when you're solving it. Try to solve it by yourself, and then if you're stuck or anything, try to figure it out from the class notes or the book. And if you cannot, then consult the solutions, right? So that way you have what you need to succeed. And I will post rest of the solutions for 4.1 and 4.2. Most of those things and solutions have been posted already, but remaining problems I will post them. And I will also try to post some more practice problems because some of you asked some solutions for some of the problems. I will post those as well. But you already have a lot of resources that you can go through. And I will say this again, you will not see any problem that we have not solved in the class or that you have not been provided a full solution to in one form or the other on the exam. So whatever you see on the exam, you should have seen full solution to that either in class or in homework or solution that is posted that I would have done and as a part of homework help section or a review section in different forms. So you should be exposed to this material at least 2-3 times. So please take as many steps as possible and prepare yourself to succeed and get the full marks on exam 3. Right? If you have any questions, please don't hesitate to email me. And then I would also like to remind you that the extra credit is posted. I so far received only one submission, which is very good. I mean, that submission, the person that submitted was very good. Not that I received one submission is very good, but so please take the extra credit opportunity if you need more points, and if you need any help or suggestions, please email me, get in touch with me because the semester is coming to a close where we have maybe 2.5 weeks left. So so make sure that you get to the place where you want to be because you still have 2 exams, exam 3, final exam, and extra credit. This is almost a lot more of the grade than what you have had in the entire course. So, make use of these opportunities because, come May 3rd, our final exam, after that is done, I won't be able to do anything, right? If you end up at 88 and you want A, I cannot do anything. But if you put in your extra credit, maybe those points will come into help, right? So, try to make use of all the resources you can. Okay, great. So in chapter 5, we started discussing about energy. And we first defined kinetic energy. Does anyone remember the definition of kinetic energy? And as you know, this is going to show up on the exam. Yeah. Right. So kinetic energy, we define this as the rate of transfer of impetus across a distance. So this has two parts. That is, if you consider, for example, two objects, there is one object here, let's call it M1, right? Then there is at the far end of the room, there is another object, let's say M2. I push this object M1, right? Then this is moving with some impetus. I push it. When I push it, I am acting on it. That is my ability to change the impetus. That is the definition of force. Force is the ability of one object to change the impetus of the other object. Right? If I'm applying a force, so the impetus is changed. Then, because this object gained impetus, it's going to move. That is, motion is change of place. So it is going to change its place from this place to another place. Right? So the object is changing its place. And as it is changing its place, wherever it is going, it is carrying the impetus it has with it. And how do we know that? We know that because when this object goes to M2 and touches M2, we see that M2 will begin to move. Because this object now, having this impetus, is able to apply a force on M2 when it comes into contact and change the impetus of M2. Right? Are you able to see that? So this rate of transfer of impetus has, rate of change of place. And then transfer of impetus. That is, the body is moving, and as it is moving, it is carrying this impetus with it. The rate of change of place is nothing but velocity, and the impetus that it is carrying, we are looking at very small impetus, dp. So what I'm saying is, I give it a little impetus. I just give it a little force, so it gets my impetus dp. We are moving v, so it is carrying this kinetic energy dk, which is equal to v dotted with dp. V dotted with dp. This is not a vector. Kinetic energy is not a vector. Are you able to see that? That it is not a vector because it involves the dot product. But there is a deeper physical reason, right? So if somebody asks you why is kinetic energy not a vector, why should it be a scalar? The answer should not be because it is a dot product. No, that's not the answer. We want kinetic energy to be a scalar. That's why I'm making up a dot product. The reason I want it to be a scalar is that using momentum, using impetus, I'm not able to capture the difference between two objects that are still versus two objects that are moving opposite to each other. For example, consider the situation where I have two objects, M1 and M2, both are at rest, versus M1 and M2, or let's just say all masses are M, just for simplicity. So this is V, this is minus V. Now look at these two cases. In these two cases, the total momentum is 0. But they're physically very, very different. In the first case, there is no activity at all, both at the still. In the second case, there is activity. They're moving towards each other. And when they hit each other, they go in opposite directions. There is activity. But when you look at it from the collision momentum conservation point of view, both these cases would appear as delta P is equal to 0. And I cannot distinguish between, which one is which. If you tell me delta P is 0, I cannot tell you whether it is both objects are at rest or both objects are moving, against each other. Are you able to see that? And this is a problem because these two cancel out because they're vectors. They're in opposite directions. It's the directionality that leads to that 0. So that's why we want to get rid of that. That's why we want to define something that doesn't depend upon direction. And that's how we came up with this energy, right? And we defined the energy as a scalar, right? As a number. And so this dk, kinetic energy, we said is V dot dP, as we saw on the last slide. And we know that P is equal to mv. This is the impetus. P is equal to mv. Or we can write V as P over m. So I can plug this back in here. So I would get dk as P over m dotted with dP. Right? And so if we want to get the full kinetic energy, we integrate. Full kinetic energy is integral of dk, which is integral of P dot dP over m, which gives us P squared by 2m, which is the same thing as half mv squared. Just two different ways of expressing the same thing, P squared by 2m and half mv squared. But the definition is that you're transporting impetus. And this kinetic energy tells you about the activity. So now, if you look at this, right, if you look at half mv squared, and you look at the first case, the kinetic energy, the total kinetic energy here is 0. Because nothing is moving. Whereas here, the total kinetic energy is half mv squared plus half mv squared, which is mv squared. So now, using this, you can distinguish which one is moving and which one is not. Because we got rid of the directionality in kinetic energy. So kinetic energy is a scalar because we want to keep track of activity, which we cannot do if we have only vectors such as momentum. So we want to keep track of activity, and because vectors do not allow us to distinguish between stationary versus things that are moving opposite to each other, we define a new scalar. Yes.
The reason why you got magnitude of P squared over 2 is because think about it in reference to x, take the integral of x, you get x squared. Is that the same multiplication?
Yeah, this P dot dP x dx is, yeah. Yes. Are you following me? Any questions? We have done this in the last lecture, just repeating it, revising it because we had a gap. Any questions so far? Are you following me? Okay. So we keep referring to these words scalar and vector. Right? We have to be a little more careful. Right? So what do we mean by a scalar and a vector? This depends upon when we look at something from different coordinate systems. So, for example, we looked at this example in one of the exams or in multiple exams, right? Where you calculate all these force vectors from two different coordinate systems, right? And clearly, the force vectors, for example, if I pick the g vector, this g vector, right? If I write the g vector in a coordinate system that is flat, that looks like x hat and y hat, then it would look like g is equal to minus gy. But if I were to write it in this kind of a coordinate system, where I have x hat prime and y hat prime, then it would look like g is equal to minus g sine theta x hat prime minus g cosine theta y hat prime. So you see that if I change the coordinate system, the way the vector appears, the components of the vector, they change. Are you able to notice that? If I change the coordinate system, the components change. So if you change the coordinate system and components change, that's a vector. If you change the coordinate system and the vector change the components change in a particular fashion, then you can call it a vector or even more a tensor and things like that, build up from there. But the critical thing for identifying a vector or a tensor, which you might learn about later, or already have learned about, is that when you change the coordinate system, the components look different. If you remember, in this problem, I asked another question, that is, calculate the dot product. For example, calculate the dot product of these two forces, like N and F. Right? So if you calculated the dot product, N dot F, irrespective of which coordinate system you calculate, what do you expect? Would it be 0?
Yeah.
I see some cases still thinking. So convince yourself that N and L are perpendicular no matter what. Right? If they're perpendicular irrespective of which coordinate system. Then they may have different components, but N dot F will always be 0. So even if you change your coordinate system, this doesn't change. That is a scalar. That is the definition of a scalar. A scalar is not a number. A scalar is something that does not change when you change the coordinate system. A vector is something whose components change when you change the coordinate system, right? So, for example, now if you were to say, the length or the height of this inclined plane, right? What do we mean by the length or the height of this inclined plane? I actually mean the measure of the length, right? So when I say the height of this inclined plane is a meter, what I mean to say is that the measure of the height of this inclined plane is a meter. But as I'm comparing it to some other object, I'm calling it a meter. Now, if you change the coordinate system, is that going to change? No, it's not going to change, right? Because it's still going to be 1 meter. But if I were to draw an arrow like this, right? An arrow like that, and write it as a vector now, that vector will change if you change the coordinate system. If you have a flat coordinate system, this vector will be 1y hat. But if you have an inclined coordinate system, it will be something else. Right? But if you take the magnitude, for example, here, the g vector, if you take the magnitude of this, right? Let's see the magnitude of this vector. How do you do the magnitude of this vector? Recall that if you have something like ax x hat plus ay y hat, we do the magnitude by taking the Pythagoras theorem, right? So here, magnitude of g would be g squared sine theta square plus g squared cosine theta square, which would be just simply be g. This magnitude doesn't change when you change the coordinate system. So scalar is something that doesn't change when you change the coordinate system. A vector is something whose components change when you change the coordinate system. So that's what we mean by a scalar, right? So the total energy should not change when you change the coordinate system. Are you able to see that now? Are you following me? This is going to be very important for what we're going to do next. So, any questions? So what do you think about dot product in general? Would any dot product change? If you change the coordinate system, would any dot product change? No, right? Because the vectors are what they are, the angle is what it is. So just because you change the coordinate system, the angle between the vectors is not going to change. The vectors are going to look different, but still the angle is still going to be what it is. Like n vector may look like something else, the f vector may look like something else, but still the angle between them is going to be 90. Following me? So the dot products are always scalars. Are you able to see that? Because in fact, we can get magnitude another way, right? How can we get magnitude another way? I can get this as g dot g, right? A dot A would be magnitude of A squared, right? So this dot product is also a scalar. The dot product will change if we change the coordinate system. Yes,
Scalars can't have the negative sign that applies a direction.
no. You can have a negative sign, and negative sign implies a lack of something, right? So, for example, like, if you owe me $5, right? Then -5, right? So that's not necessarily a direction, it's a lack of something, or you could use it in a different sense. And there are other ways you can use negative numbers, right, to reduce something. If something is losing out from the system, like for example, 10 people are entering, 5 people are losing out, right? So there is a direction there, but it is not as such this kind of a direction. There are different meanings in which we use the vectors. So if you go back to chapter 2, so there are different meanings in which we can use the negative numbers, but in general, they indicate lack of something, but not necessarily direction, unless you associate it explicitly with something. But yeah,
So how do we get from multiply negative number by itself positive?
right.
So everything that it's not good.
The magnitude is always positive,
That's
right? Magnitude is always positive. Here the magnitude is always positive, right? So
Magnitude is can't.
yeah, magnitudes cannot be negative. Right? So magnitudes cannot be negative because you're taking the modulus and it's the length or it's magnitude. So there's no negative magnitude. But I thought you were asking if there are no negative numbers as scalars.
I worded it.
Right. So for example, you have a negative temperature, right? That's not necessarily a direction, it's just a number, right? But it's but magnitudes of vectors are always positive. If that's what you're asking. Those are two different questions. Any other questions? Okay, so now we're going to define something new. So to do that, let's see. We know that from Newton's second law, we know that F is equal to dP by dt. That is, force is the ability to change the impetus of an object. So from Newton's second law, we know that F is equal to dP by dt. And we defined dk, kinetic energy, as V dot dP, right? V dot dP. But I could define V as dx. I don't want to use x. So dr by dt, r is the position vector that we are drawing to the object, right? Dotted with dp. Right, we define dk as the rate of transfer of momentum, which is v dot dp. But v is the velocity, right? So if you have the position vector, it is the derivative of the position vector, time derivative. So I have written it as dr by dt dot with dp. So now I'm going to manipulate this a little bit and write this as dr dot dp by dt. Just move the dt, from under dr to dp. Still the same thing. Right? But now dp by dt is the force from Newton's second law. So then I can write this as dr dot f. dr dot f. So I can write dk as dr dot f, which is the same thing as f dot dr, because a dot b is equal to b dot a. Are you able to follow that? This is the rate of transfer of momentum. It's just a simple manipulation of pushing the dt, right, and realizing that expressing it in just two different ways, right? One is basically writing it in terms of dt, right? And another is writing it in terms of F, the force. Just a matter of pushing this dt instead of from dr to dc. Right? Now we're going to give this a name, this f dot dr, right? Because you see that if you have some object, let's say we have some object, right? And this has some position vector, right? So I can draw a position vector to it. So let's say this is my origin. This is the position vector r of this object. Now it is at rest to begin with. Then I apply some force, right? And push it, right? Then what happens? Now I can answer this question in several different ways. That is, when I push it, I could say I have applied a force on it. So that force changes the impetus. So this object gains some impetus. And that impetus is going to be transported across. That is, there is going to be a rate of transfer of impetus across a distance. Or there is going to be kinetic energy. Follow me? With me? So that would be saying this object is going to get some kinetic energy, dk. Another way of saying it is, I have applied a force, and due to this, the object gained an impetus, and it's going to move some distance. This means I have done work on this object. I have performed some work on this object, and this work in turn translated to its kinetic energy. So we define this f dot dr as work done. So we write that as dw. Are you with me? Are you able to see what we're doing here? Just different ways of explaining it. That you could say the object gained the kinetic energy, or you could say I did work on the object. Right? Both are the same thing. So now we define this work done as f dotted with dr. Now notice that this f and dr are vectors. It's very, very important to note that these are vectors, and always make sure that you know how to handle these vectors, right? So for example, here, let's say I apply some force, right? Some force 10 newtons along x hat, right? And this object moves by a meter, right? Then the work done, dw, is going to be 10 x hat dotted with 1 meter x hat, which is going to be 10 Newton meter x hat dotted with x hat, which is going to be simply 10 Newton meter. Okay. So you have to use these f and dr as vectors. Are you with me? Now let's do another one, right? So let's say you have a ball, right? It's at a height of, let's say, 10 meters, right? It's going to fall down. What is the work done on this ball by gravity? Right? So we know that work done, dw, is f dot dr, where r is the position vector of the object. So you have to pick the forces and the directions here. So first, we will choose a coordinate system, right? So we will choose this as our x hat and y hat, right? And so I'm going to pick this as my origin. And so the ball is initially at r is equal to r is equal to 10 y hat. Right? R0 is at 10 y hat. And then it's coming down, right? And R final is going to be 0 y hat. 0 y hat. And the force of gravity, let's say this mass is 1 kilogram, but force of gravity is mass times g vector. So that is 1 times g vector is, let's say, minus 10 y hat meters per second square. So that's going to be minus 10 y hat meter per second square. And then we have RF and R0. So our dr would be RF final minus R0, right, which would be minus 10 y hat, right? RF minus R0 minus 10. Minus 10 because it increased. Yes. Thank you. So then our work done would be equal to, the force is minus 10 y hat meter per second square, right? Dotted with dr is minus 10 y hat meters, right? Kg meter per second square. So that is same thing as plus 100. This kilogram meter per second square is newtons, Newton meter. What I want you to notice here is how we are doing this dr. Right? So you have to pick where you are initially and where you are reaching finally, and you have to see the directions, the direction of motion with respect to the direction of force, right? So here, the work done is positive. The work done is positive means the object is going to gain kinetic energy. The work done is positive means the object is going to gain kinetic energy. And that makes sense because as the object is going to fall down, right, it is going to accelerate. So it's going to gain velocity. It's going to have more activity and have more impetus. So it's going to gain more kinetic energy. So if the force acting is in the same direction as the displacement, then work is going to be done on the object. So the object is going to gain kinetic energy. Are you following me? But if they're in opposite directions, if the work done is in opposite direction to the direction of motion, then the work done is going to come out to be negative. That means the kinetic energy is going to be drained. For example, friction is one such force. Friction is a force where force is always opposite to the direction of motion, right? So that's why the energy would be drained. PW would always be negative. Are you able to see that? Yes.
It's another example of drag.
Yes, drag is another example. The type of drag is just another name, but it's the concept is the same, that it's opposite to, acts opposite to motion, like friction. Are you able to see how to do why the vector notation is important? Okay. Now, let's say, if we draw maybe a bigger picture. So let's say there is somebody who is going down a hill like this, right? Like sliding down this snow or something like that, right? Now here, the person is going to slide down, right? Along the surface. So the person is going to slide down along the surface. Imagine that this is like a quarter of a circle. Imagine that this is a quarter of a circle, right? And now I want to calculate the work done by gravity, right? It is still the same thing. It is still the same thing. dW is F dot dr, right? F dot dr. Except now, I cannot really say, like how I had done before, like in the case of the object falling in a straight line, because here I could just subtract it like this because it was a straight line, right? But here, this is not a straight line. We will see that there are some forces, like for example, gravity. It's okay to still do it like you did it for straight line, although this path is not a straight line. Are you following me? although this path is not a straight line, it's okay if you start from, this is R0, and this is RF, right? Some final position and initial position and final position. It's okay if you just consider the initial and final positions for some forces. But for some other forces, it's not okay, right? So clearly, you have to always consider this path, right? So you have to be careful in how you deal with this. And you already have the tool set to do this. So how would you do this? You pick a center, right? And draw this. R is equal to R hat. Right? R is equal to R hat. So what is dr? R is equal to R hat. Dr is dr R hat plus R dr hat. Right? And that is dr R hat plus, right? I hope you remember this. I hope you have not forgotten it. R d theta hat. We just simply remove the dt underneath, right? The way we did this was, R was equal to R hat. So if you did R dot, if you remember, this was R dot, R hat dot plus plus R hat dot. Or we could write this as dr by dt is equal to dr by dt R hat plus R dr hat dot by dt. Right? So if I pick out all the dt's, are you able to see that? That is, you're not just changing straight down. As you're going along this path, you have to go along an angle, right? Slide along an angle. Are you able to see that? Have you guys done path integrals before? No? Some of you have. But the concept is this, that you're using the position vector. This dr is the change in the position vector. What that means is that if this person has come here, right, then the position vector has changed. And this change in the position vector is what you're calling as dr, right? And that is, we are able to get it from here. Are you able to see that? So you can use these kind of coordinate systems, and we will do one problem exactly using this kind of coordinate systems to find out work done. But you have to consider the path in general. For some of the forces, so there are two kinds of forces. For some of the forces, work done is independent of the path. That is, it doesn't matter whether you go, like this, or whether you fall straight down. All that matters is what is the difference between the initial and the final position. What is the initial state and the final state? Only those matter. The path that you take doesn't matter. So you can go any which way, right? And basically, it wouldn't matter. So work done is independent of the path. These forces are called conservative forces. They're called conservative forces, not because they don't like Democrats, but because they conserve energy. That is, we have seen that when I do work, that work results in kinetic energy, right? So if I do the opposite way, that is, for example, if I drop this pen, right, it's going to gain kinetic energy, right? Correct? If I drop this pen, it's going to gain kinetic energy. That is, to lift this pen up, I have done work. I have to do work to lift this pen up against gravity. Because as I'm lifting this pen up, at every point, this pen is being pulled down by gravity, and at every point I have to hold it and pull it with a certain force to make sure that it doesn't fall down, and keep doing that until it reaches whatever height. So I have done all that work, and that's how I brought it here. Now, all that work, I can get it back if I let it go, in terms of its kinetic energy. Are you able to see that? That's a conservative force. Right, that is, you can get it back. But there are other kinds of forces where work done is dependent on the path. And these are non-conservative forces. One such example is friction. Clearly, you can see this, that if you take two paths, right? Let's say you have, let's say, this is point A, this is point B, point C, point D, right? So let's say you want to go from point A to point D. Let's say you take two paths. Path one is you go directly from A to D. Path two is you go from A to B, then to C, then to D, right? So clearly, the second path, you have to travel a longer distance. That means you're going to experience more friction, which means you're going to dissipate more energy, right? So clearly, this path is not going to be same as going straight when friction is involved. Common sense will tell you that when friction is involved, A to B is not the same as A to B to C to D, right? So non-conservative forces, because they dissipate energy, the work done is being given out to the environment, it is not being stored. They're called non-conservative. That is, the work done is lost to the environment. There is interaction with the surroundings. Recall our discussion on conservation of momentum. It hinged upon the thing that there is no external force acting, but we considered everything to be internal. Right, so everything, when everything is internal, we say conserve. So if I do some work and that work is sort of going to be taken back by the body as its kinetic energy, right? Like when I let go of the pen, it's going to get its work done as kinetic energy, then it's a conservative force. But in case of friction, right, the work done by friction is gone. It generates heat, and that heat goes into surroundings. You can't get it back, right? You rub your hands against each other, right? That's it, it's gone. The heat is gone. You cannot get it back. So there is interaction with the surroundings, so it's a non-conservative force, yes. Sorry?
So you have friction, then there is no friction.
If there is friction, there is no conservation of momentum. Not necessarily, right? It depends how you consider the system, right? So there's no conservation of kinetic energy if you have friction. Momentum is always conserved, because in case of momentum, right, if we have seen this, that in case of an inelastic collision, right, the kinetic energy is not conserved, right, but momentum is still conserved. Do you remember that inelastic collision? You answered that in the exam, that inelastic collision momentum is conserved and kinetic energy is not conserved, right? Do you remember that? Momentum is always conserved because A is acting on B, B is acting back on A, and when you consider both the things, right, they sort of cancel out. So the net force is zero.
But isn't friction as, so it doesn't.
Yeah, but there is, just like the object is applying, just like the floor is applying the force on the object is applying the force on the floor too. Right? So when you consider both the object and the floor as your system, those two forces cancel out, right? So there is no net force acting on the system. So it depends where you draw the boundary and what you call as your system, right? Are you able to see what I'm saying? So momentum is always conserved no matter what, because internal forces that are acting opposite to each other cancel out. This is the whole reason why we define kinetic energy, because delta P, for example, the way we did in the beginning, right here, but delta P in both cases is zero, right? But kinetic energy is not. Are you able to see that? Right, so in a very similar way, in a very analogous way, right, in case of friction, the forces cancel out because they're action-reaction pairs, right? One object applies a force on another, and there is a reaction force, right? So they cancel out. So the total momentum is conserved, but the kinetic energy is not. Okay. Any other questions? Okay, so we will study more about conservative and non-conservative forces. So particularly, I want to focus on the conservative forces. We already started looking at one conservative force, which is gravity. We will look at another conservative force called the spring force. Right, that is, if you compress the spring, there is a restoring force. If you try to compress the spring, it tries to push you back. That is, if you take a spring, for example, and attach a mass to it, and you try to push the mass, right, it tries to push the mass back. It tries to go back to its equilibrium position, wherever it was. So if you push this spring in this direction, right, the spring tries to push back. It's called a restoring force. That is, it wants to go back to wherever it was. And so the force is given by what we call as minus kx x hat. We will talk about this more later in the next lecture. I don't want to go over it, finish it today, but I just want to give you a heads up that we're going to talk about the spring force and gravity. And from here, in case of conservative forces, we're going to describe something very, very important. We're going to come up with something called the potential energy. Right? Recall our discussion on potency. Right? Potency is something that you have that has not yet been actualized. Right? So this is potential energy, meaning, for example, when I did this work, when I lifted this pen out, right, and I'm still holding this pen, this pen has the ability to gain kinetic energy, but doesn't have the kinetic energy yet, because I'm still holding it. But if I let it go, it can actualize it and get that kinetic energy. So then I would say that this pen potentially has kinetic energy. That is, if I let it go, it can get kinetic energy. So it potentially has that. That's what I'm calling as potential energy. And if I do let it go, then I'm just going to get kinetic energy. Are you able to see that? So it's just a different way of expressing energy in case of conservative forces. And using potential energy and kinetic energy and work done, we're going to talk about energy conservation, and we will finish our discussion on conservation of momentum and conservation of energy, and solve a lot of problems in the future lectures. I know that we have covered a lot of concepts and did not solve many problems today because we have some ground to cover before we can solve some problems. So I want you to get familiar with these concepts of work done, potential energy, and stuff like that, and then we will do a lot of problems so that you can become familiar with the things. Thank you.